Hi and welcome to this video 3 on the series for Unit 4, Topic 4, Math Methods. This is on probability density functions and the normal distribution, and we'll be talking about probability density functions today, but in particular talking about the mean and expected value of probability density functions. So there's going to be a few videos for this particular section, and we're working on 16B, 16C, 16D from our Cambridge textbook, and there's our learning goals and success criteria for this particular section. So let's talk about mean and expected values. So I just want to remind you that the mean and expected value for a discrete random variable, which we did in chapter 14 and 15, is calculated by doing the expected value, which is the mean, is equal to the sum of each x data point times by the probability of that occurring. So you just get each x data point multiplied by the probability, add them all together, and bam, you've got your average, you've got your mean, you've got what you expect to get if you run this experiment on average hundreds or thousands of times. For a continuous distribution, so here's our continuous distribution. It may be different to this. There may be two functions across two domains. There may just be one function between negative infinity and infinity, or there may be multiple other things going on. But here's a bit of a generalization, where the function f of x represents the distribution across a domain C to D and at 0 otherwise. The expected value of a continuous distribution is the integral between D and C of x times the probability function x. So this probability function is our f of x from above. But we sometimes write that as a probability function as well. So there's that interchangeability between f of x and p of x in this case. So it looks a lot like the discrete one, x and x, p of x and p of x, except now we've got this function. The expected value of x, and I'll write about this blue line and this blue bit here, is equal to the integral between d and c, which could be infinity and negative infinity if it's a continuous function across all numbers, of x times f of x, which is the probability density function with respect to x. So it matches our discrete random variable expected value. And what's even better is that this will be a fairly integratable value. The problem here is that we don't just do a summation, because with a continuous random variable there's an infinite number of possible values as opposed to the discrete number of possible values from earlier topics. So we can't do a summation, but we can do a summation of an infinite number of possible values through the integration technique. This is what this does. It calculates the area under the curve, and if we do x times that particular x times the probability of that x occurring for every possible value and sum them up, then for an infinite number of values this is integration. So there's the formula. Let's put it into practice in example 1. So in example 1, I want to calculate the expected value of x of the probability distribution that's given there. Fourth this x brackets 2 minus x for the domain 0 to 2. And so the expected value of x will be equal to the integral between 2 and 0 of x times 4/5 x 2 minus x dx. And that will be equal to expected value of 2 to 0 of 4/5 x squared 2 minus x dx. And you can integrate polynomials. You'd expand that bracket and integrate the cubic and the quadratic that comes with it. But in this case, I'm going to just quickly remind you how to do it on here. So we come in here, we go to math, we go across F6, then we choose the integrate. Inside the function, we've got 4/5 x squared brackets, was it 2 minus x or x minus 2? X squared brackets 2 minus x, 2 minus x close brackets, and then we go from 0 to 2, and we get 16 over 15. Now this is an expected value, so it doesn't have to be between 0 and 1. It's not a probability, it's an expected value. 16 over 15 is pretty close though, but remember, I don't know exactly what the function looks like. Original function was a cubic, but it's in the range 0 to 2, so it looks something like this. We don't know a great deal about it, except that our expected value should be somewhere between 0 and 2, and it's 16 over 15, which is a little bit greater than 1. That makes sense. We're happy with that. So there is a calculating the expected value of a probability density function, just using that formula. We might just talk quickly about variance and standard deviation while we're here as well. So recall that for discrete random variables, the variance is equal to the expected value of x squared minus the expected, oh, that is incorrect, my apologies, the expected value of x squared minus the expected value of x squared. That's better. And so the variance is equal to that formula. That's what we use for discrete. It's one of the versions we use for discrete. The other version we used for discrete was here. This is the one we used in a table. This is the one that's usually a little bit easier to work out, particularly if you already know the mean. It's going to be the same in this case. That's going to be a little bit easier to work out if you know the mean. So for a continuous distribution, the probability is equal to f of x, where x is between c and d, or 0 otherwise, same as above, except this time we're doing the variance. So this time, instead of between d and c of x px, we get the integral between d and c of x squared dx. X squared instead of x because it's e to the x squared, e of x squared, not e of x. And we have to subtract the expected value of x all squared. Remember, the expected value of x is also known as mu. So don't forget that the expected value of x represents a mean, which is written as mu, or sometimes, not often in this topic, sometimes written as x bar as well. So we've got mu, mean, expected value, sigma, standard deviation. That's usually the easier way, but this is the other way as well. On the formula sheet, this is what you have. And so I just want to make a note of this. On the formula sheet, you're told that information, and this is just the expected value. Now, this isn't too bad because mu will be known. In this case, mu is 16 over 15. We calculated that in example 1 when we get to the second example in a second. And so it's actually very doable. It's just x minus that and then squared. It just becomes a little bit more complex a function. To integrate, we end up with that 16 over 15. Sometimes we end up with an even more complex number in there. So I think this one up here is a bit easier if you can deal with that. But this is what you're given in your formula sheet. And of course the infinity and negative infinity can be exchanged for if there's a clear domain C to D. But in this case we've got infinity and negative infinity. And of course the standard deviation, if you ask for it, is the square root of variance. And that's sigma. Variance is sigma squared. And so we just take the square root of the variance formula. So let's have a quick look at example 2. But before we do, I was going to get a brain transplant, but I changed my mind. And that is just an example of the types of hilarious jokes I'm going to start putting into my videos, just to see if you're paying attention. So example 2, calculate the variance of x, or the variance x of the probability distribution function given here. And so the variance x is equal to the integral between c and d, which is 2 and 0, of x squared. I'm going to do it this way, but you should get the same answer doing it the other way. 4/5 x, 2 minus x dx minus 16 over 15 squared. That's my mu squared. So I'm going to use that formula. And I'm going to go to here, and I'll put that in. Now, I've done the previous question to get 16 over 15, so I'm just going to use that. I know that if I multiply by x squared instead of x, that's just going to create a cube here. Probably shouldn't have done that. A cube there. And of course I need to subtract from that 16 over 15 squared. And I get a variance of 32 over 225. So I'll go back and I'll just pop that down. 32 over 225. And if I wanted to calculate the standard deviation, this of course is sigma squared. That's what variance is. Sigma, my standard deviation, would be equal to the square root of 32 over 225. And a bit to keep things exact, that's equal to 4 root 2 over 15, whatever that is. So there we have it. That is the mean, variance, and standard deviation of a continuous random variable probability density function. There's 6 nice big long words all strung together. All the best.